For part 1 of chapter 7, we're going to explore atoms, elements, and moles. Let's start by defining matter. So what is matter made of? In ancient Greece, they thought there were just 4 Greek elements: earth, fire, wind, and water. But in 1661, Robert Boyle came along and proved through experimentation that there were actually many more elements than ancient Greece originally predicted. Today, elements are defined as substances that cannot be broken down any further by chemical means. Each element on the periodic table is composed of atoms that have the same atomic number. Democritus actually took it in a slightly different direction. Instead of focusing on the elements, he focused on the ultimate components of all substances. Now, this ultimate component he coined as the atom, which is Greek for atomus, which means uncuttable or indivisible. So what an atom is it's the smallest particle of an element that retains the properties of that element. So elements are essentially made up of atoms. John Dalton came along and devised the first modern atomic theory, which we'll look at next. The first modern atomic theory had 5 main postulates that we're going to cover. The first 2 postulates later proved not to be entirely true, and we'll look more closely at that when the time comes. The very first postulate is that elements consist of tiny, indivisible particles called atoms. So it's true that elements consist of tiny particles called atoms, but what we'll see is that it's not true that atoms are indivisible. For number 2, all atoms of an element are identical. Now, identical is a strong word. All atoms of an element are very similar. For instance, we'll see that they have the same atomic number, but they can differ in other ways. So that's why number 2 isn't entirely true anymore. However, these were true at the time that John Dalton came up with this theory. For number 3, a particular element's atoms are different from another element's atoms. Well, that's true. Carbon atoms would be different from oxygen atoms. Still proven true today. For number 4, compounds consist of different atomic elements combined. That's just the definition of a compound. If you have 2 or more elements forming a bond of some sort, it's going to be classified as a compound. The examples shown below are sodium chloride, where we have sodium forming a bond with chlorine, and then of course water, where we have hydrogen and oxygen atoms combining. Number 5, atoms are neither created or destroyed during a chemical reaction, but rearranged. And we'll see this when we start balancing chemical equations. So it's just like with energy as well. Energy is not created or destroyed, it's just transformed. Same goes for atoms in chemical reactions. So let's look at Rule 1 and why it has been disproved. So what's true about the first postulate is that elements are composed of atoms that have the same atomic number. That's still proven true. What's also still true is that atoms are the smallest particle of an element that retain the properties of that element. The false part of that postulate is that atoms are indivisible particles. That is not true. Atoms are not indivisible particles. We can actually split atoms now with technology that we've learned. Let's look at the composition of an atom. So atoms consist of 3 subatomic particles. They're called subatomic particles because they are the 3 particles that make up the atom. We have a proton, a neutron, and an electron. Now, protons are positively charged particles. Neutrons are neutral, hence the name neutron, which means they do not have a charge, or a charge of 0, you could say. And then electrons are going to be the negatively charged particles. So where are these subatomic particles in an atom? Well, Ernest Rutherford did some studies, some experiments to discover the structure of an atom. And what he found through his experiments were that the volume occupied by an atom consists of a large amount of empty space, which we later find out that this is actually the electron cloud. Then there's a small positively charged center that has most of the mass of the atom. This center is called the nucleus. Now, to put this a little bit in perspective, when we talk about the nucleus versus this large electron cloud, the nucleus would be the size of a blueberry, and the electron cloud around it, that empty space that he's talking about, would be the size of a football field. So here are two depictions of atoms. We can see the center, that nucleus, the blueberry we were just talking about, in both. So in the picture off to the left, we have just a red center, being the nucleus. Over in the picture to the right, the nucleus is the center still, but you can see the individual subatomic particles that are in the nucleus, which are the protons and the neutrons. Now, the electron cloud on the outside, that's where the electrons are. And the electrons are actually orbiting that nucleus in the center, traveling around it. Look a little bit closer at the nucleus of an atom. So atomic nucleus contains of what we call nucleons. So a nucleon is just another word for protons and neutrons together, because that's what's in the nucleus, are just the protons and the neutrons. So the overall charge of the nucleus is positive, because we said that protons have a positive charge and neutrons have a neutral charge. So since the nucleus is made up of protons and neutrons, you could see that the center, the nucleus, is positively charged. Due to this positively charged center, the electrons are attracted to it because opposites attract, and that's why they orbit around the nucleus. Here's kind of a summary of those charges and also the masses of the three subatomic particles contained in an atom. So we have the proton, which we said was located in the nucleus, and it had a +1 charge. Now the actual mass of a proton is 1.00727. For our purposes, we're just going to round that to a whole number and say the mass is 1. Neutrons, the other subatomic particle located in the nucleus, have a charge of 0. They're neutral. Their mass we're also going to round to just a whole number and give it 1. Now for electrons, electrons are present in that electron cloud surrounding the nucleus. So they are outside of the nucleus. They have a -1 charge, is why they're orbiting the nucleus, that positively charged center. Now their mass is relatively small. It's 0.00055. So since it's so small, we say it's negligible. And when we're calculating mass of atoms, we're going to count the electrons as having a mass of 0, so they're not going to count towards our mass measurements. Now let's look at the elements. So atoms, which we've just discussed, are made up of 3 subatomic particles: protons, neutrons, and electrons. And atoms themselves make up elements. So when we're looking at elements on the periodic table, they're represented by atomic symbols. And not all atomic symbols make sense for the name of that element in English. For instance, sodium is represented by the symbol Na. And the reason it's represented by the symbol Na and not S or SO is because the symbol came from the Latin word natrium. Tungsten has something similar. It's represented by the symbol W for wolfram in Swedish. Just be aware when you're trying to find some of these elements on the periodic table that the symbol doesn't always match up with the name itself. Looking at atomic number. So on the periodic table, elements are represented by a symbol, which we just discussed on the previous slide. So in this top example, the symbol would be C for carbon. What else is represented on the periodic table is the atomic number. And the atomic number is usually represented as a whole number above the symbol. So in this top case, it would be 6 for carbon. Now that number 6, that atomic number, actually represents the number of protons in carbon atoms. So that means all carbon atoms have 6 protons. If you change the number of atoms, or if you change the number of protons, you're actually changing the identity of the element itself. So let's look at the second example. In the second example, we have molybdenum represented with the chemical symbol MO. Now the atomic number is the whole number above the symbol, 42. So what this means is molybdenum has 42 protons. So all atoms of molybdenum will have 42 protons. If you change the number of protons, you're changing the identity of the element itself. Next, let's look at mass number. So mass number is a number that's not represented on the periodic table. And we're going to calculate this by adding the protons and the neutrons together. Because remember that table that we looked at previously, protons were worth 1 atomic mass unit and neutrons were also worth 1 atomic mass unit. So if we know the number of protons and neutrons, we can just add those together to get the total mass number. Let's look at some calculations involving the mass numbers. So in this example, we're going to determine the mass number of an iodine atom that has 73 neutrons. Well, notice they gave us the number of neutrons, but we just said on the previous slide that for mass, we need the neutrons and the protons. So how do we figure out the number of protons? Well, what we would do is we would look up iodine on the periodic table, because remember, the number of protons is represented on the periodic table right above the element symbol. So looking at iodine, its atomic number is 53, which means its number of protons is 53. So to solve for the mass number, we would take 53, the number of protons, and add it to 73, the number of neutrons. Remember, we don't need to know the number of electrons because since their mass is so small, it doesn't count towards the total mass number. So adding the protons to the neutrons, we get a total mass number of that particular iodine atom at 126. Let's try a few more. So in these three examples, we are given the subatomic particles. So we have protons, neutrons, and electrons. Now remember, when you're trying to calculate mass, the electrons aren't going to count towards mass. So you want to ignore that last piece of information. So to solve for each one of these, you're simply going to add the protons to the neutrons for each one. So in the first one, we have 13 plus 14, which should give us a total of 27. 37 for the next, and 56 for the last one. So why are we counting mass numbers? How is that important? Well, mass numbers are important when we're looking at isotopes. So to define an isotope, isotopes are atoms of the same element that differ in mass number. So for instance, we looked at an example of iodine atoms and we calculated the mass number of a particular iodine atom. Well, all iodine atoms are going to have the same number of protons. That's the atomic number that we saw represented above the element symbol on the periodic table. So if we're talking about iodine, all atoms of iodine will have 53 protons. That's not going to change. However, there can be other atoms of iodine that have a different number of neutrons. And because they have a different number of neutrons, their mass number is going to change. Because remember, mass number is the protons plus the neutrons. So the protons might be the protons might remain the same, but the neutrons could change, which affects that total mass number. So bringing it back to the first modern atomic theory, we said number 2, postulate 2, was not entirely true. And why is this? It's because of isotopes, actually. So we said all atoms of an element are identical. And we just said, because of isotopes, that all atoms of an element can differ in their mass, meaning they wouldn't be identical. Their mass numbers can be different from one atom to another. Let's look more closely at isotopes. Elements can have multiple isotopes that occur naturally, each with a different number of neutrons. Remember, the number of protons are staying the same. It's the number of neutrons that is changing and making that mass number different. So here's an example of isotopes of neon. So there are 3 different isotopes of neon: neon 20, neon 21, and neon 22. So with how they're written, we have the element name, and then after the dash, the number that comes after the dash, that's their mass number. So neon 20 would have a mass number of 20. Neon 21 would have a mass number of 21, so on and so forth. So if we wanted to calculate the number of protons and neutrons in each of those isotopes, the protons would be the same for each one of those. For all 3 of those isotopes, it would be the number of neutrons that would differ. So looking at an example, neon 20, it would have 10 protons because the atomic number of neon is 10, just like all the other isotopes of neon, but it's the neutrons that change. To figure out the number of neutrons, we just need to figure out what plus 10 is going to equal that mass number. The isotopes represented occur in a certain abundance. So notice we said that mass number was not represented on the periodic table. The number that is represented on the periodic table is the average atomic mass, and that's a decimal point, not a whole number. So for neon, the average atomic mass is 20.19. And the reason, or how they calculate that, is by taking all 3 isotopes of neon and their abundance and calculating out the average atomic mass of all atoms of neon. So how are isotopes found, and how is the abundance counted? So how do we come up with that average atomic mass? They actually use what is called a mass spectrometer, and this separates atoms by differing masses. And since it's separating based off of their mass, it's actually isolating the isotopes. It can give the relative abundance by counting each isotope at that mass in the sample. So looking a little bit closer at how a mass spectrometer works. You have a sample of neon, for instance, and it's hit by an ion beam. When that ion beam hits it, it actually knocks some of the electrons off of the atom, making the atoms positive. Because remember, electrons are negatively charged particles, so if we knock any of those off, it's going to make the atom an overall positive charge. Having this positively charged ion now, those atoms go through a magnet. Now this magnet is curved. And this magnetic field, what it does is it actually separates all of those atoms based off of their mass. So around the inside of the curve is where the lowest mass atoms are going to curve to. The outside of the curve is where the highest mass atoms are going to gravitate towards. There's a sensor at the end of the magnet that counts the atoms as they come out. So the ones that went the shortest path would come out first, and those would be the lowest mass atoms. The ones that went the longest path around the outside of the curve would be the heaviest and would be counted last. So once you have the sample go through the magnet, what you get out is a mass spectrum that looks kind of like the picture here, where we have mass number on the x-axis and the ion beam intensity on the right. So how they calculate the abundance is they actually take the area underneath each of these peaks. You can see there's a peak at 20, and that's the largest peak on this spectrum. And there's a reason for that. When you look at neon 20, its abundance is 90%. What that means is 90.6% of all neon atoms have a mass number of 20. There are 2 other peaks, but they're very small. You can see a tiny, tiny peak at 21, which accounts for this neon 21 isotope. And notice the abundance on that, it's only 0.26%, barely a blip, which makes sense when you see the peak itself with how tiny it is. A slightly larger peak at the 22 mark represents the neon 22 isotope with a 9% abundance. Averaging these out give you an average atomic mass for neon of 20.19. Here's just a cutout of some other isotopes that you'll find in a table in your OpenStax books. You'll notice that almost all elements have isotopes to them. Beryllium would be one exception. So notice beryllium just has one isotope, but all others have 2, possibly 3, some even 4 different isotopes. So isotopes are represented in 2 different ways. We've seen one way so far, and that first way that we've explored is where we have the element name and then a dash with the mass number coming after the dash. So an example would be carbon-12. This 12 is saying that the mass number of that particular isotope is 12. The other way to represent isotopes is using a nuclide symbol, and that's what we see in this white box off to the right. So in a nuclide symbol, we write the element symbol from the periodic table. So in the case of carbon, we would use the letter C. And the number in the upper left-hand corner is the mass number. So in this case, 12 would be the mass number of that carbon isotope. The number below, that's the atomic number, or the number of protons. This number is sometimes omitted when we write a nuclide symbol because we could find out the atomic number simply by looking up carbon on the periodic table. So let's calculate the number of protons, neutrons, and electrons using some nuclide symbols. So here we have a nuclide symbol of chlorine. Now remember, this number in the upper left-hand corner, that's the mass number of that particular isotope. This number 17 is the atomic mass number, or the number of protons, I should say. So using this nuclide symbol, 17 represents the number of protons. So that makes that part easy. For the number of neutrons, we're actually going to take the mass number and subtract the number of protons from it. So it's kind of nice when we're using a nuclide symbol to calculate the neutrons because they have it set up for us. They have the mass number of 35 in the upper left-hand corner. So all we need to do is add a subtraction sign right here. And to figure out the number of neutrons, we take 35 minus 17. Mass number minus protons. To figure out the number of electrons, well, all of the isotopes that we're going to be exploring are going to be neutral. What that means is they're not going to have a charge. So if there is no charge, the protons equal the electrons. And we know this because protons are positively charged, electrons are negatively charged. So in order for that overall atom to be neutral, the positives and negatives have to cancel each other out. So if I have 17 protons, that must mean that I have 17 electrons. Let's look at another example. So here's another nuclide symbol representing an isotope of magnesium. So we have a mass number of 26, and then they give us the atomic number of 12. The atomic number is the number of protons. Since it's a neutral molecule, that means we also have 12 electrons. To calculate the number of neutrons, we simply subtract the mass number of 26 minus the number of protons of 12 to get a total of 14 neutrons. Here are some more examples. Determine the mass and identity of an atom with the following particle counts and write the nuclide symbol. Now we're going to go through and do these ones in class. However, I do want to quickly point out a few steps in beginning to solve these. So if you're trying to calculate mass, remember you're just looking at the protons and the neutrons. When we write a nuclide symbol, we write the symbol with the mass number in the upper left-hand corner and the number of protons in the lower left-hand corner. To figure out the nuclide symbol, or the symbol that we're going to represent, it's the number of protons that's going to help us figure that out. And we'll see that in the lecture class video. So we've looked at mass number mainly. where we're using the protons and the neutrons to come up with a mass number, and that's a whole number. And the mass number differs between isotopes. So isotopes, once again, being atoms of the same element with different number of neutrons, making their mass numbers different. Average atomic mass, we haven't covered very much so far. What average atomic mass is it's that number on the periodic table underneath the chemical symbol. It's not a whole number. It's the weighted average of the atomic mass of all the isotopes of that specific element. So let's look a little bit closer at the average atomic mass and what we're going to use that for. So the average atomic mass on the periodic table, so for this carbon element, it would be 12.011 would be the average atomic mass. We're going to be using the average atomic masses to calculate molar mass. Molar mass is also known as formula mass. If you wanted to follow along in your OpenStax book, we're looking at Chapter 6, Section 1. So molar mass is the sum of all the atomic masses of the atoms represented in a chemical formula. So if you wanted to calculate molar mass, you first need a chemical formula. So we have some chemical formulas represented here. The first one is the chemical formula for water. So this symbol H is telling us that hydrogen is present in that compound of water. This symbol O is telling us that oxygen is also present. Now, the number that comes after each of these elements, the subscript that comes after each of these elements, tells us how many atoms of that element are present. So for instance, in H2O, since there's a number 2, a subscript of 2 after the hydrogen, that means there are 2 atoms of hydrogen in this compound. For oxygen, there is no number, no subscript after oxygen, so we assume it to be a 1. Which means there's 1 atom of oxygen. The next example is copper 2 chloride, and we'll learn how to name these compounds in a later section. Right now, let's just look at the formulas and how to tell how many atoms of each element are present. So Cu is copper. There is no number, no subscript after the element symbol, so we assume there's just 1 copper atom. Cl is chlorine. The subscript of 2 tells us there are 2 chlorine atoms present in that molecule. The next example is C6H6. So we have carbon and we have hydrogen present in this compound. How many carbons? 6. How many hydrogens? Looking at the subscript tells me 6. So we're going to be using these chemical formulas to help us calculate the molar mass, along with the atomic mass that we can find on the periodic table. So let's look at how this is done. To calculate the molar mass of a compound, for each element present, you need to take the number of atoms, represented by the subscript in the chemical formula, and multiply it by the atomic mass, which you find on the periodic table. Then you add the molar masses of each element together. So looking at an example of CHCl3. So this is the chemical formula. I like to start by making a list of all elements present. So we have carbon, hydrogen, and chlorine. So I have my list of carbon, hydrogen, and chlorine. Next, I make a list of how many atoms are in each of those elements. And to figure out the number of atoms of each, we're looking at the subscripts. So carbon doesn't have a subscript after it, so we assume there's just 1 carbon atom. Hydrogen, same thing, 1 carbon atom. Now chlorine has a 3 after it. So that little number 3, that subscript, tells me there are 3 chlorine atoms. Now for the next column, we're looking at the atomic mass. And this is that average atomic mass that can be found on the periodic table. So when you find carbon on the periodic table, you'll see that its atomic mass is 12.01. For hydrogen, it is 1.008, and then chlorine is 35.45. Now Now you need to multiply across. So for carbon, there's one atom that has a mass of 12.01. Hydrogen, one atom with a mass of 1.008. Chlorine, there's 3 of them this time, so 3 times 35.45 gives us 106.35. Now for the total molar mass of that entire compound, we need to add the carbon to the hydrogen to the chlorine, and we get a total of 119.37, and the units are grams per mole. On the previous slide, we said the units when we calculate molar mass were grams per mole. Now, mole is a unit or a term that we haven't looked at yet in this course. We're going to look at the mole in Avogadro's number. So what exactly is a mole? A mole is the SI unit for the amount of a substance. So when we talked about SI units in Chapter 1, the International System of Units, the mole is the unit for the amount of a substance. This mole amount was devised by chemists so that they could count chemical particles simply by weighing them. And we define the mole using Avogadro's number. So Avogadro's number is 6.022 times 10 to the 23rd. So if we have 1 mole of a substance, any substance, it could be an element, a covalent compound, or an ionic compound. In that 1 mole, there's going to be 6.022 times 10 to the 23rd particles. So what do I mean by particles? Well, if I'm talking about an element, particles are going to be atoms. So elements, we said, are made up of atoms, and we can actually calculate, if we know how many moles we have, exactly how many atoms we have in a given sample. If we're talking about compounds, instead of the word atoms, we use the word molecules or formula units. The calculation is the same, Avogadro's number is the same, it's just the term used after it that is different. So why do we use moles? Well, atoms and molecules have a very small mass. They're very, very, very tiny. And it would be much easier to count large numbers of them doing a calculation than it would be to physically count them. I mean, look at Avogadro's number, for instance. 6.022 times 10 to the 23rd. It's written in scientific notation. It has a positive exponent. So that positive exponent of 23, that's saying you're going to move this decimal point 23 times to the right, making this a huge number. Now, would you want to physically count that many atoms? Well, first you'd need a powerful microscope, a lot of patience, and you would probably lose count several times before getting it correct. So instead of actually physically counting them, we use a calculation to figure out how many atoms are present in a particular sample. So how are we going to be doing these calculations? Well, we're going to do them in the same way that you would do calculations if you were using the term dozen. So what the term dozen means is 12 of something. It could be 12 eggs, 12 donuts, 12 pencils, basically 12 of anything. So you can use this word entities and replace it with whatever particular object you are talking about. So dozen means 12 in the same way that the word mole means 6.022 times 10 to the 23rd. It just looks scarier because it's such a large number. So if I were going to calculate how many eggs were in 3 dozen, to figure that out, I would take 3 and multiply it by what the word dozen means. And we just said dozen means 12. 3 times 12 tells me there are 36 eggs. Now, let's apply this using the term moles. So if I wanted to know how many atoms were in 3 moles, I'm going to do the same type of calculation. I'm going to take the number 3 and I'm going to multiply it by what the word moles means. And moles means 6.022 times 10 to the 23rd. So plugging that in and multiplying it out, we get 1.806 times 10 to the 24th atoms. Now, when we're calculating using Avogadro's number, the word entities can be atoms molecules, or formula units. So here are the equations that you'll see on your equation sheet for doing conversions using molar mass as well as using Avogadro's number. So we have several different types of calculations we might come across when given word problems. One, going from grams to moles. So if you are asked to solve for the moles of something and you are given the mass and the molar mass, to solve you would take the mass in grams and divide it by the molar mass. Now remember, molar mass you will most likely need to calculate. The units on it are grams per mole. When you calculate the molar mass, you need the chemical formula and the periodic table. To calculate from moles to grams, given the mole amount, you're going to take the amount of moles given and multiply it by the molar mass. Next, let's look at some calculations using Avogadro's number. Now, how do you know when to use Avogadro's number? If you see the word atoms, molecules, or formula units at all in the question, one of these two equations will be used. So number of particles. When I say the word particles, what I mean is you're going to see either atoms in place of particles, molecules, or formula units. So if you're asked to solve for the number of atoms, molecules, or formula units, you're going to take the mole amount and multiply it by Avogadro's number. If you're asked to solve for the number of moles, you're going to take the number of atoms and divide it by Avogadro's number. We'll do a lot of these calculations during class period. Here's a flowchart summarizing those calculations. So those equations on the equation sheet that you saw on the previous slide help us go between mass in grams, to moles, and then to atoms or molecules. So if you're going from mass to moles, this direction, you're going to divide by the molar mass. If you're going from moles to mass, the opposite direction, you're going to multiply by the molar mass. In order to figure out the number of atoms or molecules, you need to have the mole amount. So how many moles? So given this moles amount, if you needed to figure out the number of atoms or molecules in that given substance, going this direction, you multiply by Avogadro's number. If you are given the atoms or molecules starting here, and they ask you to solve for the moles, you're going to go the opposite direction and divide by Avogadro's number.